Dear students, welcome to the lecture 3, which deals with hexadecimal number systems and some other concepts. So, uh, as I said, hexadecimal numbers plays a vital role in uh, computer arithmetic. So, if you understand how to represent an hexadecimal number of a decimal, then it will be very easy for calculating the arithmetic operations on hexadecimal numbers. So this particular lecture deals with, or you will be able to convert hexadecimal numbers to other number systems and vice versa, compute binary arithmetic results, find the ones and twos complement, and represent negative numbers using ones and twos complement. The hexadecimal number system is most commonly used in a computer data processing, where we know the range of hexadecimal numbers are 0 to 9 and A to F, the base is 16. And if you state how the hexadecimal numbers are represented for the corresponding decimal numbers, up to 9 it is same, and 10 is represented with A, 11 B, and so on up to 15 F. After F, you will be getting 1 0 in hexadecimal, and that is equal to 16 in decimal. And in the binary format, you can easily find, if you know the decimal, you can easily find the binary. Hexadecimal converter. So the concept is same as we discussed for octal to decimal. Octal, the weight is 8. Here, hexadecimal, the weight is in the powers of 16. Right? So simply multiply the weight into corresponding digit, you'll be getting decimal equals. And in a reverse fashion, divide with 16, write down the remainder. Suppose if the remainder, if you get 16, sorry, 14, write its hexadecimal equivalent, but don't write 1 4 as answer. Because in hexadecimal, what is the question? Convert 350 to hexadecimal. Divide with 16. Quotient is 21, remainder is 14. And 14 is represented as E in the hexadecimal. So like this, we have to follow the same process as we have done for octal to decimal and decimal to octal. Now, hexa to binary and binary to hexa. It is somewhat similar to octal to binary and binary to octal. As we discussed, every octal digit is equivalent to 3 bits of binary, but every hexadecimal digit is equivalent to 4 bits of binary. So suppose, for example, convert hexadecimal number to binary. Here the hexadecimal number A, the binary equivalent is 1010. Another hexadecimal digit E, the binary equivalent is 1110. So the final answer would be 1010 and 1110. So this is what the binary equivalent of hexadecimal. So the same process applied in reverse by grouping together 4 bits. Suppose if the question is asked binary to hexadecimal, the process is same, but start splitting from LSB, that is rightmost bit. This is said to be LSB. Suppose here the question is given 11100100 101. This is the binary number. Convert it into hexadecimal. So start splitting from the right side to 4 bits because it is binary to hexa. And if here there are only 3 bits, you append 0, the value doesn't change. So this is 6, this is 2, this is 5. So the final answer is 16. Right? So this is how we convert binary to hexa and hexa to binary. And then hexa to octal, it is also very simple. First convert hexadecimal to binary, then binary to octal by grouping into 3 bits. For example, 1A316. So this is an hexadecimal. Represent each digit with 4 bits in the binary. Then start splitting into 3 bits. Right? So this would be the answer. This is how hexa to octal and octal to hexa. You can do in a similar fashion. So without converting it into decimal, you can also perform like this. If you use a decimal, you can also follow the process like hexa to decimal, then decimal to octal. But it takes more time for calculating, right? If the numbers are like this, it takes very time for finding the answer. But this process is very simple, converting it into binary, then binary to same octal to hexa. First, 76 is given, convert it into binary, represent in 3 bits because 76 is an octal, and then split into 4 bits because we need to get in the hexadecimal format. And then binary arithmetic is also very, very important. If the 2 bits are added, what is the result? And what is the sum and carry? So 2 bits, 0 plus 0, sum is 0 and carry is 0. Overall result is 0. 0 plus 1, sum is 1, carry will be 0. Overall result is 1. 1 plus 0, sum 1, carry 0, overall result. 1 plus 1, this is very important. Sum is 0, carry is generated as 1, and the overall result is 1, 0. So if you take 2 examples, 1, 0, 1, 0 plus double 0, double 1, 1 plus, sorry, 0 plus 1, 1, 1 plus 1, sum is 0, carry is generated here. 1 plus 0 plus 0, sum is 1, carry is 0, no need to write that. 1 plus 0, 1. So this is the overall result. This is also another example you can work out on this. So final result is a 5-bit result. In the subtraction, there would not be addend and augend, there would be minuend and subtrahend. So 1 minus, or 0 minus 0, difference is 0. Borrow is not required. And the difference among these two is 1. But here borrow is required for this because subtrahend is greater than minuend. So definitely you require borrow. If borrow is required, you place 1. If borrow is not required, you place 0. So 1 minus 0, difference is 1, borrow is not required, so 0. 1 minus 1, difference is 0, borrow is not required. So same example, right? You can perform the subtraction and you can verify this result. You can pause the video and you can verify this particular result. And negative numbers and their arithmetic. So every negative number is represented in the 3 quadrants. So sorry, first is sign magnitude, next 1's complement, next 2's complement. So this comes the first sign magnitude, 1's complement, and 2's complement. So what is 1's complement? Replacing ones with zeros and zeros with ones. That's it. Suppose, for example, 1's complement of 0, 1, 1, 0, 1 is there. This is 0 is replaced with 1 and 1 is replaced with 0. And this will be the answer. Very simple. Or subtract original number with ones. Both are same. We'll be getting same result. Or replacing ones with zeros and vice versa. And 2's complement means once you get 1's complement, add 1 to that, you'll be getting 2's complement. Very simple. To the 1's complement, we'll be adding 1, we'll be getting 2's. So you can cross-check this result. You can pause the video and cross-check the result. And what happens if you are doing 2's complement 2 times? Suppose if this is a number 1001, the 2's complement of this is 0,111. Again, if you do the 2's complement, you will be getting 1001. So these two are same. So if I write 2's complement of x, and again if I perform 2's complement of same. So if I perform 2's complement 2 times, I will be getting x. So x may be any bit pattern, right? And so on. So to represent a negative number using complement, the process involves the 2 steps. First is Obtain binary representation of equivalent positive number and take the appropriate complement of a representation. So first represent in a positive manner, positive number, and then do the complement. So this is how the changing the sign of the number gets modified. Suppose if I want to get 1s and 2's complement of representation of -5, -7, first what is +5? How it is represented? 0, 1, 0, 1. Right? So 0 indicates a plus. 1 indicates in the leftmost bit is 0, it is a positive number. This is also referred as most significant. So 0, 1, 0, 1 is +5. Do the 1's complement. This is nothing but -5 in 1's complement. And if you do the 2's complement of this +5, not 2's complement of 1's, 2's complement of +5, this will be -5 representation is 2's. Similarly, you can work out on -7. Then these are some of the examples already we have discussed, but these are fractional numbers. Go through this, you can easily understand. And some examples are given predicting the base of a number system. Right? So this also very simple. Instead of giving the base here 8 to 16, here the base is given as b. You need to predict the value of b, and this is the process of finding the value of b. Similarly, you work out on these examples, and we'll be discussing the solutions of this in class. With this, in the next lecture, we'll be discussing subtraction using 1s and 2's complement. With this, the lecture 3 is concluded. Thank you, students. Thank you.